In this video, we're going to take a look at fluid force. We start out with the pressure that is applied to an object. So the pressure on an object at depth h in a liquid is equal to W times h, where W is the weight density of the liquid and h is the depth that the object is underneath the liquid. So pressure is simply a weight density times a depth. Now, just so we're aware, water has a weight density of 62.4 pounds per cubic foot or 9,800 newtons per cubic meter. Those are two common numbers that I will use. If we are talking about some other liquid, then those other liquids will have different weight densities. And if we do a problem with another liquid besides water, then I will give you the weight density in the actual problem. But pressure on an object is simply weight density times depth of whatever liquid we're in. Now we transition from pressure to the concept of force. Imagine that the object is a horizontal plate. So we have a horizontal plate and we want to find the force applied on this horizontal object. What we do to find the force being applied to that horizontal object is simply multiply the pressure times the area of that object. So if we have a horizontal object, then all of the pressure is going to be the same because all of the points on that object are going to be at the same depth. And therefore, we can just multiply the pressure times the total area of the object, and we would get the fluid force. That is the force of the liquid on that object. So let's do an example. Imagine I have a 3 by 3 foot square plate submerged in 5 feet of water. How much force is being applied to that square? Basically, what we do is we take the pressure, which is again weight density times depth. Depth here is 5 feet. And then we multiply it times the area. Well, this is a square, so the area is going to be just side times side, which is 3 by 3, which would be 9 square feet. So let's do those calculations. So here we go. So we have our horizontally oriented 3 by 3 square plate submerged in 5 feet of water. It is horizontal, so it's flat. How much force is being applied to that square? So force is equal to pressure times area. Area is 3 feet by 3 feet, so that's 9 square feet. Pressure is going to be the weight density of water, in this case, times the depth of the water. So we got weight density times the depth. We said the depth is 5 feet, and the weight density is 62.4 pounds per cubic feet when we're talking about feet. So it's the force is just this multiplication, 62.4 times the depth times the area, which is 2,808. By the way, if you keep up with the labels, 62.4 is pounds per cubic feet. So we take pounds per cubic feet. The depth, that 5, is in feet, and the area is in square feet. So what's happening is that when you keep track of all of the labels, you can see that the feet, when we take depth times area, become cubic feet. That is going to cancel out with the cubic feet in the denominator of the weight density. And my ultimate label is just pounds in this case. So we are getting the same measurements of force that we got in previous sections. So there it is. Now, if you think about this, so 9 came from 3 by 3. The fact that the area of this square plate was 3 by 3. If you look at this 5 times 3 times 3, that is actually just the volume of this cube of water that's above the square. So notice these lines here. If I just took that cube, the volume of that cube would be 5 times 3 times 3. So in some sense, all we're calculating is the volume of the water directly above this plate times the weight density. So if we have those things, then we can figure out our force. Our force is just, again, volume of the water above times weight density. So it really doesn't matter whether or not this is in some big lake or if this was in just a really deep tub or if this were in a swimming pool. That force is going to be just a product of essentially the water straight above the plate, the amount of water straight above the plate. All right, so what if our plate is not horizontal, is not flat? What if we turn our plate in other directions? Well, if we turn our plate in other directions, we're going to have to use something called Pascal's principle. And Pascal's principle says the pressure at a point in a fluid at rest is the same in all directions. So at rest just means we're not in a stream where there's currents. If there were currents, then there might be more pressure in one direction than the other. But if we have a fluid at rest, then the pressure is the same in all directions. So if I dropped a tiny marble into the water, the top pressure and the bottom pressure and the side pressure on that marble are all going to be the same. So pressure is the same on all planes passing through any specific point. That's what Pascal's principle says. And hopefully that makes sense because of when you're in a certain liquid, that object is going to be experiencing pressure from all sides in all directions. So that's Pascal's principle. That allows me to say that if we have a vertical orientation, then any point on that vertical orientation is going to experience the same pressure as it would if it were horizontally oriented, if that point were horizontally oriented. So what we're going to do to find the fluid force on a vertical plate is we are going to break up that vertical plate into really small horizontal slivers, and the force applied to each one of those horizontal slivers is going to be pressure times area. And then we let the width of those slivers go to 0. And if we do that, then that's going to turn into an integration. And when we, again, do the Riemann sum, and then that Riemann sum as the width of the slivers go to 0 turns into an integration. Now, because we're doing really small horizontal slivers, if you think about the XY axis, and let's just say some vertical plate, horizontal slivers are going to have width with respect to Y. So all of our integration is going to be with respect to Y. And what's the force gonna depend on? Well, pressure is gonna depend on weight density multiplied times the depth. So wherever the water line is, down to Y. And then the area, well, each of these slivers is gonna have some sort of a length. Obviously I drew a square, but the length times width is going to give me my area of each of these little slivers. So that leads me to my fluid force formula. The formula for the fluid force exerted on a vertical plate is weight density integrate from C to D h of y times L of y dy. H of y is going to be the depth, how far each one of those horizontal slivers is under the water or whatever liquid we're using, times L of y. That's going to be the length of each of those rectangles. So integrate depth times length of rectangle, all with respect to y, and then multiply times the weight density. Weight density is going to be a constant, so you can pull that out front. That is the fluid force formula of how much fluid force is being exerted on a vertical plate. Again, I'm using Pascal's principle to be able to say force, the pressure is being applied in all directions evenly. So let's do an example with a rectangular plate submerged in water. Find the fluid force on the vertical plate submerged in water that we see in this picture. So here we have a 4x3 rectangle. 3 is the height, 4 is the width. It is 3 feet under water. So the top of the rectangle is 3 feet under water. Now, each and every time we do a problem like this, we are going to have to create some sort of Cartesian coordinate grid on top of my picture. You can put the origin at any place. So I could put the origin somewhere out here in no man's land. I could put the origin at one corner of the rectangle. I could put the origin at the water line. We're going to, in general, put the origin at the most convenient spot in each problem. And each problem, most convenient spot may have may be different. So we have to put our Cartesian coordinate plane somewhere in this picture, put our origin, orient the picture in alignment with the Cartesian coordinate plane. So where are we going to put our origin? What I'm going to do is I am going to put my origin at this lower left corner here. And then my y-axis is perfectly aligned with the left-hand side of the rectangle, and my x-axis will be perfectly aligned with the bottom of that rectangle. Okay, there's a reason I'm doing that. Now, if I do it this way, if I orient my rectangle the way I just did, then the vertical line on the right-hand side of the rectangle is the line x equals 4. Because we're 4 feet away. The top of the rectangle is 3 feet up. So this would be a horizontal line. The horizontal top of the rectangle would be y equals 3. And the water line would be 6 feet up. That would be y equals 6. Now I'm ready to put the stuff in for my integration. So weight density, this was in water. So weight density is 62.4 pounds per cubic feet. I'm using that number, the 62.4, because all of my measurements were in feet. So 62.4, and then I'm going to integrate from a y value of 0, that's the bottom of the rectangle, to a y value of 3, because that is the top of that rectangle. So we're integrating from 0 to 3. The depth. Now here's where you have to be pretty careful. If I draw some sort of rectangle in here, it's going to be at some arbitrary y value. The depth of this rectangle is going to be 6 minus y. So it's from the water line, which we said was y equals 6, down to some arbitrary value for y. So 6 minus y is the depth of the rectangle. The length of the rectangle is going to go from x equals 4 on the right-hand side to x equals 0 on the left-hand side. So once again, 6 minus y is the depth of an arbitrary rectangle, and the length of that rectangle, again, goes from x equals 4 down to x equals 0. I just have to integrate this. Obviously, you can do this by hand if we'd like, but as usual, I will just plug things into my calculator. When I plugged things into my calculator, I got 3,369.6. That would be in pounds because of the same thing we did earlier. We are taking a value, we're going to take my h of y, the depth is in feet, L of y, that's the length of rectangles, that's in feet, and then this integrate with respect to y, that's going to be also height, which is in feet. So feet times feet times feet times weight density, which is 62.4 pounds per cubic feet. The feet all cancel each other out, and you just get 3,369.6 pounds. So that's how it's done in this case. Now, this case was really easy because we were dealing with a rectangle, and so our vertical line was x equals 4. Notice we were writing that as x is equal to a function of y. And rectangles, obviously worked fairly easy because I could put the origin at the lower left corner of that rectangle. We'll show some other ways to orient things in the next problem. Now, an interesting thing that I wanted to show you was the connection between this and our previous problem of submerging a horizontal object. This is a very nice object to submerge vertically and look at it horizontally as well. This object is symmetrical about the middle of that object. So there's a symmetry right here in the middle of the object, where above and below are mirror images of each other. So imagine that on that line of symmetry, I took and I rotated this object to make it horizontal. If I made it horizontal on that line of symmetry, that line of symmetry is obviously 1.5 units, 1.5 feet from the bottom and 1.5 feet from the top of the rectangle. Think about what the fluid force on that horizontally oriented object would be. The pressure would be weight density, 62.4 pounds, multiplied times the depth. Now, again, we're taking and rotating it around this line of symmetry. So that is a depth of 3 plus 1.5. So that's a depth of 4.5. And then the area of this object would be 3 by 4. It's a 3 by 4 rectangle. It turns out that if you do that calculation, you get exactly 3,369.6 pounds as well. So essentially, what we're looking at here is that the fluid force can be obtained by the integration, and it's the same fluid force that you would get as long as you essentially rotate this along the axis, which is like your center of mass axis. I won't get into that, but this is a center of mass idea. Hopefully that makes sense, because while the pressure is going to be a little bit lower above there, going to be a little bit higher below there, if you rotate that, it'll kind of even out. I typically don't do this calculation. I just do the integration calculation and leave it at that. Let's do another example. This example, we won't deal with a rectangle anymore. We'll deal with a triangle. We want to find the fluid force on this vertical plate submerged in water. This triangle is a right triangle whose bases are 7 by 4, and the tip of that triangle is 3 feet under the water. Once again, the first thing I need to do is put my origin somewhere on this picture so that I get a good Cartesian coordinate plane on top of this. Some people might use the lower left point to put the origin. It's actually going to be a bit easier if you use this top point as the placement of the origin. You'll see why in just a moment. So that's what I'm going to do. I'm going to put the origin right here at the top point, and then my y-axis will run even with the left-hand side of my triangle, and my x-axis will be right here. I think that will give the best picture. Now, the thing we have to understand, now that I've done that, what this right-hand line is going to be, it's going to be a line through the origin. And lines through the origin are pretty easy to see. The line is going to be y equals mx plus b, but since we're through the origin, it's just going to be slope times x because b will be 0. So y is equal to slope times x. Slope of that line is down 7 over 4. So y is equal to negative 7/4 x is that right-hand side line. Now, we don't want this to be y equals negative 7/4 x. We want this as x equals a function of y because we're going to be integrating with respect to y. So if I solve that for x, I just need to multiply times the reciprocal on both sides. So multiply times negative 4/7. And that's the right-hand side line. The left-hand line is going to be the y-axis, which is just x equals 0. So I get x equals 0 as one side of a horizontal rectangle. And on the other side of a horizontal rectangle, I get x equals negative 4/7 times y. Now, the bottom of the triangle is 7 feet under 7 feet under the x-axis. The top of the triangle is right at the x-axis. So when we integrate, we're going to go from a negative 7 up to a 0. So that's y equals negative 7 to y equals 0. And then we're going to have our depth of our water is going to be, our water line is at 3 feet above the x-axis. So it's going to go from 3 down to y. So we're going to go 3 minus y. Be careful, these y's are negative. So if we do 3 minus 1, we're at 3 minus negative 1. We're at a depth of 4. That's what we want. So we're subtracting a negative. We're getting more than 3 feet in terms of depth. So that's how I would orient this. Again, this line here is the x equals negative 4/7 times y. That's that line here. So now I'm ready to fill out the integration. Again, origin is right here. I had to clear those things off to start writing here, but we're going to go from negative 7 up to 0. The depth was from 3 feet down to a y. Those y values will be negative, so that's perfectly fine. And then the length of the rectangle, the right-hand side is x equals negative 4/7 y. And we're going from there down to x equals 0. We're submerged in water, so our weight density is going to be 62.4. And that's the integration I get. I could, if I wanted to, do that by hand, but it's going to be a lot easier with my calculator, so I'll just use my calculator. When I did the calculations, I ended up with 6,697.6 pounds as my answer. 6,697.6 pounds. as the fluid force being applied on this triangular plate submerged 3 feet underwater. Just like in the last example, if you wanted to, you could draw a line at the center of mass and then put that plate vertically, put the plate from vertical to horizontal, excuse me. So switch the plate from vertical to horizontal by flipping it on its center of mass and then doing the depth times weight density times area calculation. We're not going to do that on this one, not in this section anyways. But that's what you get. Now, some other person may have put the origin at another spot. You could imagine somebody putting the origin down here, and that would have been fine as well. If I put the origin at the lower left hand corner, then this vertical line becomes my y-axis. The horizontal line at the bottom of the triangle becomes my x-axis. Here's the deal. This equation is a little bit harder to get in that scenario. This equation would be a line which has slope of -7/4. So the equation of that line would be y equals -7/4x. But then it would not cross at the origin, so we'd have to add 7 because it crosses at the point 0, 7 in this case. If you convert that, what you could do, you could let subtract 7 and then multiply times the reciprocal. Notice that we're going to get -4/7 times y, and -4/7 times 7 times -7 is a positive, times -7 is a +4. Yeah. So that would be the right-hand side line of a rectangle that you draw. That rectangle would go on the right, on that line, and on the left, it'd be x equals 0 once again. So here's the setup. 62.4. In this case, if I let my origin be at that lower left-hand corner, we're going to start our integration at 0 and end at 7 because that's the top of the triangle. The depth, well, the depth now is, the water line is at 10 feet down to some arbitrary y value. So the depth is 10 down to some arbitrary y value. And the length is going to go from, on the right-hand side, this line, -4/7 times y plus 4, down to x equals 0. So we'd get this formula for fluid force if we put the origin at the lower left-hand corner. Now I'm gonna once again do this with my calculator. So I'm gonna type in all of the expression. It turns out if you type in the expression here, if you orient your Cartesian coordinate plane with the way we described, you get the exact same fluid force. So regardless if you orient your Cartesian coordinate plane at the top point of the triangle or the lower left corner of the triangle, or you could have oriented it on this right corner, or you could have oriented it where the origin is somewhere out in space here. As long as you do the correct integration with your orientation, you'll get the same answer. So 6697.6 pounds. Again, I tend to like this way better because it's just less work than using this equation. If I can get things through the origin, lines through the origin, then the more lines through the origin I have, the better. So that's when I have things like rectangles and triangles and so on and so forth. Let's do another example. Let's say we submerge a vertical plate in water, and the vertical plate is the right-hand side of a circle. So it's a semicircle, but the right-hand side of a semicircle, whose radius is 2 feet. And the top of that circle is 3 feet under the water line. Now, in this case, we don't have a nice straight line. We have a circle. So where do I want to put the origin? The natural place when we have a circle to put the origin is the center of the circle, because then the circle equation is x squared plus y squared equals radius squared. So that's what I'm going to do. I'm going to submerge this plate in water. I'm going to orient my Cartesian coordinate grid such that the center of my circle or the center of my semicircle is at the origin. All right, so let's go ahead and do this. Water weight density is 62.4 pounds per cubic foot. That'll tell me what to put into the W. We're going to integrate. Well, if I allow the origin to be the center of the circle, then the circle is going to have equation x squared plus y squared equals, radius is 2, so you're going to get 2 squared, which is 4. Now I have to solve that thing for x, and if I do, let's actually solve it this way. If I solve for x, x squared is equal to 4 minus y squared when I subtract y squared from both sides. And then because I'm dealing with the right-hand side of the circle, that means all of my x values are going to be positive. So when I take and solve for x, I can take the positive square root of 4 minus y squared. So that's going to be the right-hand side of this circle, or this right-hand side of the semicircle. The left-hand side of the semicircle is going to be my y-axis, or x equals 0 line. Now I just have to figure out where to integrate to and from, and then my depth. Well, if I am putting the origin here, and I know the radius is 2, then we're going to be integrating from y equals -2 at the bottom to y equals a +2 at the top of my semicircle. The depth is going to be, well, if I draw a representative rectangle, we're going to be at some arbitrary value of y. How far under the water is this y? Well, the origin, as you can see, you go 2 up to hit the top of the circle, and then 3 more. So the water line is at 5. So the depth is going to be 5 minus some arbitrary y value. And now we're ready to put things in. So here we go. Let's take this and start plugging in some numbers. Again, weight density, 62.4 because we're in water. My integration is going to go from -2 to +2. The depth of the water is 5, the depth of a horizontal sliver is going to be 5 minus that arbitrary y value where the sliver's at. And then the rectangle has right-hand side of square root of 4 minus y squared. And the left-hand side of that rectangle is x equals 0. So with putting the origin at the center of the circle, or the center of the would-be circle, then we get all of this stuff. Now I'm ready to integrate. This is just, again, a calculator function. So integrate 62.4. Let me say that. 62.4 times the integration from -2 to 2 of 5 minus y times quantity square root 4 minus y squared minus 0 integrated with respect to y. Now, once again, we're talking about square roots. As I plug in like -2 and +2, we're getting, if I do this by my calculator, we're getting square roots close to 0, and that might throw the rounding just slightly off. That's okay. I'm getting 1960.35 pounds. By the way, that is approximately 624 pi pounds. And with the same argument I had from before, remember that if we're talking about center of mass, well, the center of mass of this circle is going to go right through the center of the circle. So what would the depth be? The depth would be 5. If I took this semicircle and flipped it so it is horizontal right along this line, I would take and find fluid force by 5 times 6. Well, let me restate that. 62.4, the weight density of water, times the depth, which is 5, times the area. Well, the area is 1/2 times the area of a circle of radius 2. So that's 1/2 times pi times radius squared. And sure enough, if I do that calculation, I get 624 times pi. I shouldn't say it's approximately. This is actually perfectly equal. The calculator gives me a rounding error a little bit, so the calculator won't say exactly 624 pi, but it should be exactly equal to 624 pi. And again, I'm doing 62.4 times the depth, which is 5, times the area, which is 1/2 of a circle, 1/2 of pi times the radius squared. And you'll get the exact same thing. Again, we do it here. We do by the integration because oftentimes on certain pictures, it's hard to find the center of mass and that line of center of mass. Imagine on the triangle trying to find the center of mass, it would take you a minute. Here it was very obvious where the center of mass is because there's symmetry. With the rectangle we did in the second example, it was obvious where the center of mass was because of symmetry. But not everything is going to be so exact or so easy to find center of mass. But when we can, we see that it's the same. So there we go. Let's do another example with a semicircle, but this one is not going to be vertical. This one is going to be the bottom half of a circle. So find the fluid force on this vertical plate submerged in water. It's the bottom half of a circle. The radius of the circle should be 3 meters. The depth of the water is 6 meters, and that is 6 meters above the top of that semicircle. And the semicircle is the bottom half of the circle. By the way, notice that we're in meters now. So we need to change our weight density from being the 62.4 pounds per cubic foot to the 9,800 newtons per cubic meter. All right, so once again, I am going to put the origin at the center of the would-be circle. So that means at the top of this semicircle. So I'm going to put the origin right there. That way I have a nice equation for the circle. The circle is going to be x squared plus y squared equals 9 because the radius is 3. So 3 squared is 9. And then when I solve for x, it turns out that the right-hand side of this circle is going to be the positive square root, but the left-hand side of the circle is going to be the negative square root. So x is equal to the positive square root of 9 minus y squared on the right-hand side of the circle. And on the left-hand side of the circle, it's going to be equal to the negative square root of 9 minus y squared. And that's going to be important because when I draw one of those representative rectangles, that's a little horizontal sliver, the right-hand side of the rectangle is going to be at the positive square root, and the left-hand side of the rectangle is going to be at the negative square root. Now, again, we're in meters, so I want to change my weight density of water to be 9,800 newtons per cubic meter. Again, that's just a number you can look up. Or, again, that'll be given to you on the test if it's a different liquid other than water. Water is something you can look up on the notes. If it's some other liquid, I would give the weight density of that liquid. Now the water line clearly is 6 meters above this center of the circle, so therefore it's 6 meters above the origin. And now we're ready to go through. Weight density is 9,800. Radius is 3, so the bottom of this semicircle is going to be at -3. The top of the semicircle is going to be at 0. The depth is 6 down to some arbitrary y value. And then the length of the rectangle is going to go from the positive square root of 9 minus y squared down to the negative square root of 9 minus y squared. If you wanted to combine that, since you're subtracting a negative, you're actually just adding those two things together. And you get 2 copies of that square root. So if you wanted to rewrite that, you could easily do 2 copies of that square root. We've done that before. So that's the idea. Again, that all depends on us putting our origin right here at the center, and then the x-axis and the y-axis are there. So we'll clear that. Now I'm ready to type this into my calculator. 9,800, integrate from -3 to 0 of, again, make sure this, you type it in right. The 6 minus y needs to be in parentheses, as well as the 2 times the square root of 9 minus y squared also needs to be in parentheses. When I do that, I get, I should say it, this is an approximation, approximately 100, excuse me, not 100, 1,007,665 0.42. That would be newtons. Let me put in some commas so that it makes it look a little bit nicer. And that's not a really nice number if you divide that by pi, because you think, well, this area is going to have something to do with pi. Yes, that area has something to do with pi, but also so it doesn't turn out to be like a whole number times pi, because when you think about the center of mass of this thing, the center of mass is not going to be at a nice, even spot. It's going to be at some weird value where half of the circle is area above and half is area below. Center of mass kind of calculations. So it's not going to be in a nice spot, and it's not not going to work out very neatly. So anyways, we get this ugly number. That's the whole point. 1,007,665.42 newtons. Let's do another example. And this example is going to work a little bit differently. So instead of submerging a plate underwater, let's imagine that we fill something up with, well, not water, but in this case, concrete. But you could have also filled it up with water. So let's fill up a tank with, in this case, concrete. Well, it turns out the fluid force applied to the side of a tank is going to be calculated the exact same way that the fluid force submerged in the liquid would be. This comes from exactly what I was saying at the very beginning, where when we take an area, let me say that again. When we take a plate, we submerge it horizontally. The amount of pressure is just going to be at each point, no matter what direction we're at, it's going to be the same because of Pascal's principle. So the pressure is going to be the same at each point. And then it doesn't matter whether this thing is in a gigantic ocean or whether it's in a gigantic lake or whether it's in a really small bathtub. The only thing that's going to matter is how much water is above the object. In this case, it was water. But in any other liquid, it would be just how much of that liquid is above the object. So when we go to this example, each point is going to have the same pressure as if it were submerged in concrete rather than the tank being full of concrete. It's the same calculation. So that's what we're going to do. So we're going to assume we have a tank and we filled it up with concrete, and the tank looks like this. It is it's a triangular shape side of the tank, and it is 6 foot across at the top, comes down to a point at the bottom, and the height of that triangle is 7 feet. Now, concrete, in this case, concrete has a weight density of 150 pounds per cubic foot. It's a lot more dense than water. So let's go ahead and find the fluid force applied on this, exerted on this side of the tank. Now, once again, obviously we're same type of calculations, but since we're in feet and weight density of the concrete we're using is 150 pounds per cubic feet, we're setting it up this way. And I essentially pretend that, well, not pretend, I pretend that what I was having in my previous examples as the water line now is the concrete line. So is the top of that tank. Now, where do I want to put my origin? You could put the origin right here, but notice that if you put your origin at the bottom tip of this triangle, then both lines of a rectangle, see, both lines at the end of the rectangle are going to both go through the origin. So that's going to work out a lot nicer if I do it that way. So that's what I'm going to do. Origin is at the bottom tip. That is going to mean one of the lines is going to be y is equal to, well, on the right-hand side, I'm going up 7 and then to the right 3. So y equals 7 over 3x. That's the right-hand side. Let me do that. So the right is y equals 7/3 x. And the left is going to be y is equal to, we're going up 7 and to the left 3. So that's going to be negative 7/3 x. I need to solve each of those for x, which is really easy if the line goes through the origin because I just have to multiply times the reciprocal. So solving for x, I get x is equal to 3/7 times y on the right-hand side. And on the left-hand side, solving for x, I get x is equal to negative 3/7 times y. So that's the right-hand side and the left-hand side of my rectangle. My origin starts at 0. So we're going to be integrating from 0 all the way up to 7. That concrete line is obviously 7 units or 7 feet above my origin. And then the depth is going to be from 7 down to arbitrary y value. Notice that's kind of always the operation for calculating the depth. It's the top of the water line, or in this case, the concrete line, down to some arbitrary y value. So let's put all of that stuff in. Weight density, 150 pounds per cubic feet. We're going to be integrating from my origin all the way up to the top of the triangle, which is 7 feet above the origin. The depth is from 7 feet down to some arbitrary y value, 7 minus y. And the length, we're going from the right-hand side, that is 3/7 times y, down to the left-hand side, which is negative 3/7 times y. If you want to combine these or make that subtracting a negative a plus, you can. If you don't, that's perfectly okay as well. I think I am going to combine just so that I 3/7 y plus 3/7 y becomes 6/7 times y. You can tell that this wouldn't be very difficult. This wouldn't be super difficult to do by hand. It'd be pretty straightforward, but I'm still going to use my calculator in order to do this. I type all of that into my calculator, and I get an answer that is 7,350. In this case, we're dealing with pounds because it was weight density in pounds per cubic feet. So 7,350 pounds is the fluid force applied on this vertical side of the tank when it is filled up with concrete. Obviously, if it were filled up with a different liquid, if it were filled up with water, we would just change the weight density. If it were filled up with ethanol, we just change the weight density. If it were filled up with mercury, we could just change the weight density. This calculation, the integration calculation, is the same no matter what liquid we're using. The only thing that changes is the weight density, depending on what the liquid you use is. So if we change the liquid, we just change the weight density. Everything else stays the same. And then if we're submerging our vertical plate or we're filling up some tank and this vertical plate represents the side of the tank, then it's the exact same. So this is the calculation in this case. Let's do another concrete example. By concrete example, I mean one where we're filling a tank with concrete and we're looking at the fluid force exerted on that vertical side of the tank. So we take a tank and we want to figure out the fluid force exerted on the vertical side of a tank. We're going to assume we're filling this tank with concrete, and that vertical side is a half of a circle, specifically the top half of the circle. And notice that on the bottom here, it says that the diameter of the circle is 10 feet. Be careful there, that's diameter is 10 feet. That is not the radius. The radius, therefore, would be 5 feet. Let's do this calculation. All right, so once again, we're going to put our origin right at the center of the circle. Circle has radius 5, so we know how to orient the circle. We know how to solve for x. And once again, when I draw a rectangle, just kind of like a couple of examples ago, the right-hand side of the circle is going to be the right-hand side of this rectangle. The left-hand side of the circle is going to be the left-hand side of the rectangle. And so we'll get a positive square root for the positive side and a negative square root for the negative side. But that's the idea. Everything is radius 5. So when we integrate, we'll integrate from 0 up to 5. Y values go from 0 up to 5. The depth Well, again, the line at the top is going to be 5 units up. So we're going to take our depth to be 5 minus arbitrary y value. And then the length of a rectangle is going to go from right side of the rectangle to left side, that's positive square root, down to the negative square root. So let's go ahead and do that. First off, oops, we do x squared plus y squared equals, again, radius is 5. Be careful about that. Radius is not 10, radius is 5. 10 is the diameter. So if I solve for x, the right-hand side is going to be the positive square root of 25 minus y squared. The left-hand side is going to be the negative square root of 25 minus y squared. So now we're ready to set up my integration. Concrete has a weight density of 150 pounds per cubic foot. We're going to be integrating from the bottom of the circle, which is a y of 0, to the top of the semicircle, which is a y of 5. The depth of the concrete is always going to be 5 minus arbitrary y value. And then, once again, we're taking the square root of 25 minus y squared as our right-hand side, minus the negative square root of 25 minus y squared as my left-hand side of the rectangle. Generally speaking, when I end up with an integration like this, I combine those square roots. Minus a negative is like adding another square root. That gives me 2 square roots. So I usually write it this way. Once again, if I integrate this, we might get some rounding errors because we're close to 0, but they're not going to be very significant. So I will use my calculator and give probably an approximate answer. So I'm going to just go ahead and type that into my calculator right now. And obviously, anytime you're typing into your calculator, make sure that you don't make a silly mistake, like not putting parentheses around both of these two terms, or typing in an incorrect number, or so on and so forth. I ended up with approximately 16,952.43, and that would be in pounds of fluid force applied or exerted on the side of this tank filled with concrete. So there we go. By the way, I just wanted to point out, if this tank wasn't completely full of concrete, let's say the tank was only this full, let's say it's 4 feet deep or 4 feet filled up, then we could do the exact same thing. We would just have to change our depth from a 5 to a 4, and we would, in this case, change our bounds from a 5 to a 4 as well. So if you're completely full with concrete, that's one thing. You can also calculate the fluid force applied to the tank if it's not completely full. If only if it's only 4 feet full, or if it's only 3 feet full, or however you'd like to measure that. But there you go. This is 16,952.43 pounds when it is completely full of concrete. Let's look at another example. So here we have a weird shaped figure. This polygon, the left-hand side of this polygon is a total of 6 feet. The bottom of this polygon is 8 feet. The right-hand side this is supposed to be 3 feet. It's supposed to match up over there. And then the top of it is this diagonal line. So let's say this is the tank and it's full of ethanol. Now, ethanol is liquid which has a lower weight density than water. Its weight density is 49.27 pounds per cubic foot. So let's try to find the fluid force on the vertical side of this tank as long as it is full of ethanol. In this case, what we're going to do is we're going to break the fluid force up into 2 parts, because if I have a representative rectangle that's down here in the rectangular portion of the tank, then the right-hand side is going to be this vertical line, and the left-hand side is going to be this vertical line. However, in the upper part of the tank, if I have a representative rectangle, the right-hand side is going to be this line, and the left-hand side is going to be the vertical line. So we're going to do 2 fluid force calculations. And moreover, you don't have to put the origin at the same place for each calculation. We'll do the fluid force of the rectangular portion, and then the fluid force of the triangular portion. And again, we can put the origin at a different spot in both of these. So when we do the rectangular portion, that's the bottom part of the tank, I'm going to put the origin right here. Now, with the bottom part of the tank, I still have to realize that the top of the tank has again, we call it the water line, or in this case, the ethanol line, because we're using ethanol, is 6 feet above the origin. So for the rectangle fluid force, I'm going to put the origin right here, lower left, and I'm going to integrate from 0 to 3. My depth is going to be from 6 down to arbitrary y value. And my rectangle is going to be right-hand side, which is, see how it's 8 units over. So that is going to be an x equals 8 down to the y-axis, which is an x equals 0. So that's what we're going to do for the rectangle. Rectangle, fluid force. Let me just copy and paste this. Weight density, 49.27. We're going to integrate from 0 to 3. The depth of that arbitrary rectangle is 6 down to arbitrary y. and then the length goes from x equals 8 to x equals 0. Again, this one's a pretty nice calculation. 49.27 times the integration from 0 to 3. Again, in parentheses, 6 minus y times quantity 8 integrated with respect to y. I got 5,321.16 pounds. Now that's the rectangle. Now I'm going to do the triangle. And when I do the triangle, I'm going to utilize a different origin. When I do this upper triangle, I think I'm going to put my origin right here at the top so that this line becomes y equals -3 over 8 times x. Or if I say y equals -3 over 8 times x, then x is equal to -8 over 3 times y, multiplied by the reciprocal. And then my integration is going to go from -3 up to 0. And my depth is going to be at 0. Notice the top here of the ethanol line, the full ethanol, is going to be at 0 down to arbitrary y value. So down to arbitrary y value, that's my depth. So that's what's going to happen with the triangle. I'll have to, oh, that's going to move with me. So I'll have to adjust that. All right, so triangle. Weight density still, since we're in ethanol, 49.27 pounds per cubic foot. Like I said, our origin is going to be at the top of this, so integrating from -3 to 0. The depth with this orientation is 0 down to y. Now our y values are all negative, so this does make sense. The depth is going to be a positive number. And then, like I said, the line on the right-hand side of this rectangle is going to be y equals, go down 3 and over 8, so -3/8 x, or when I solve that for x, that would be x equals -8/3 times y. So that's the right-hand side of the rectangle. The left-hand side of the rectangle is x equals 0. That is the y-axis. And so this is what we get. We can simply type that into our calculator if we'd like. I will type it into my calculator, I should say, and get an answer. Integrate from -3 to 0, essentially -y times -8/3 y integrated with respect to y. Again, this is easy to do by hand if you'd like. So we get 1182.48 pounds. So the fluid force on the rectangle is this 5,321.16 pounds. The fluid force on the triangle portion is 1,182.48 pounds. Notice that the rectangle is a lot more because the depth was a lot more. It's lower down. And The triangle is less. It's higher up, and also there's less area there. Now we have to, we're asked to find the total fluid force. And so that's just going to be the sum of the two. And when you add those two things together, you get 6,503.64 pounds. So if we have a situation where when you draw rectangles at one place, the right-hand side cutoff or the left-hand side cutoff is different than at another place, then you may have to use two integrations. You may have to break up your object into different pieces. And then we just calculate the fluid force of each of those pieces, add them up. Total fluid force is going to be that number. Again, this tank was full of ethanol, so we used 49.27 pounds per cubic foot. Obviously, if it was full of concrete, we'd have a much different number. We just have to change the weight densities out front. Let's do one more example. And this one is going to be one where a car crashes into a lake. And we're trying to open up a door on this car. So the car is such that the top of the door is 1 foot below the water line. The shape of the door is approximately this shape that we're given below, that we're given here. It looks like a trapezoid on top of a rectangle. Let's say that we're trying to push the door open. How much force would it take to push the door open? Or in other words, how much force, fluid force, is there on the door from the outside? Okay, so in this case, once again, we have a rectangle and a trapezoid. And basically, let's do these, we have to do them separate. With the rectangle, we'll do a standard point down here at the lower left corner. The water line is 1 foot above the top of the door. Now, notice that the door is 2.1 plus another 2.1 plus, so the door is 4.2 feet tall, plus another foot is going to be 5.2. So the water line is going to be up here at 5.2 if I put my origin at the lower left-hand corner. Obviously, we're going to be integrating from 0 up to 2.1, and then any slice rectangle is going to have right-hand side of x equals 2.5 and left-hand side of x equals 0 if I put my origin there. So that's what we're going to do with the rectangle. Weight density, this is water, it said we're falling into water, is 62.4. We're going to integrate from 0 up to 2.1 because that's the top of the rectangle. The depth goes from 5.2 down to an arbitrary value of y. And the length of the rectangle, again, x equals 2.5 on the right-hand side, x equals 0 on the left-hand side. So the force applied just to that rectangle can be calculated this way. 62.4. The integration is going to go from 0 to 2.1, 5.2 minus y multiplied times essentially just 2.5. When I type that into my calculator, I got 1,359.54. Again, that would be pounds. Now the trapezoid is a little bit different. When I deal with the trapezoid, I have to set my origin somewhere. I think what I'm going to do is I'm going to set my origin right at this corner. Now, I want to notice something, that the top of the trapezoid is 2.2 feet. And so if you look straight down from the corner to the bottom, that's going to separate this into 2.2 feet and then a 0.3 feet, because we know this rectangle has 2.5 feet total. So we get 0.3 feet there. So if I set my origin here, then this line is y equals negative 2.1 over 0.3. But this left-hand side line is x equals a negative 2.2 because it's 2.2 feet to the left of the origin. So this line is negative 2.1 over 3, has slope negative 2.1 over 3. This line is just the vertical line, x equals negative 2.2, if I set my origin there. So that's what I'm going to do. You could have set your origin here, but it's kind of a harder line to find. You could have set your origin here as well, but at the lower right-hand side of that trapezoid, that's tough. If we do set our origin at the upper right-hand corner of the trapezoid, then the water line is y equals 1, because it's 1 unit above, 1 foot above the top of that door. Hopefully that all makes sense. Now I'm ready to set up and complete the integration. So weight density, 62.4. Bottom of the trapezoid, since I put my origin at that upper right-hand corner, the bottom of the trapezoid is a negative 2.1. And the top of that trapezoid is at a 0. The depth, like I said, the water line is 1 unit down to some arbitrary y value. Again, y value here. And then the length goes from the right-hand sideline to the left-hand sideline. Remember I said, I'm going to do this. The right-hand side line is y equals, you go down negative 2.1 and over 0.3. By the way, 2.1 divided by 0.3 is 7. So that's the same thing as y equals negative 7x. Or, since I want to write x is equal to a function of y, x is equal to negative 1/7 times y. So that's the right-hand side. And then the left-hand side, if I made my origin at this upper right-hand corner, the left-hand side is going to be 2.2 units to the left. So x equals negative 2.2. So my length of the rectangle goes from negative 1/7 y down to x equals a negative 2.2. You can do this by hand in a fairly straightforward manner, but again, I tend to use my calculator. So go ahead and do that. Type it into your calculator, just practice, obviously, if you want to. And I got about 638.16. That's a rounded answer, 638.1648, if I'm a little bit more precise. So the total fluid force is going to be the sum of those two, which is, I'll do an approximate, 1,997.70 pounds. That's the water pressure on that side, the force being applied to one side of that door. This is why if a car is goes into a lake, it's going to be very, very hard to open the door if there's still air inside the cabin of the car. Once water gets on both sides of the door, then that force is being applied to both sides of the door, and it's a lot easier to open the door of the car. And that's what people generally recommend. You break the window and you crawl out the window, or you roll down the window as your car is going into the water and then crawl out the window. Because if you don't, then trying to force the door open is just way too hard as long as there's air inside of the vehicle. We're talking about, 2,000 pounds of force being applied to the outside. But again, once the interior of the vehicle fills with water, then that force is being applied to both sides, and so it's much, much easier to open the door. Okay, and there's lots of videos on YouTube about escaping from outside of a door. I've linked one of them to that picture. So there we go. So math can be useful. Tells you it's very hard to open a door if one side has water on it and the other side does not. Well, that is the calculations of fluid force that we were going to look at in this section. So that is the end of the fluid force section.